Okay, hello. Welcome to this webinar on the topic of mesh adaptation with Pointwise and ANSYS CFX CFD solver. My name is Nick Wyman. I'm Director of Applied Research at Pointwise. We're joined today by two expert panelists. Steve Carman is a member of the research staff at Pointwise as well, but spent a long career at Lockheed Martin and at University of Tennessee, Chattanooga, where he worked on solver development. And also we're joined by Paul Galpin of ISIMQ. Paul is a well-known CFD researcher. He started work with George Wraithby at University of Waterloo and then was co-founder of a company which brought vertex-based finite volume methods to the market under the TaskFlow and ANSYS CFX name. So hello, Steve.
Hello.
Hello, Paul.
Hey, Nick.
Okay, we want to thank everyone for joining on this subject. We do have a few prepared slides, but we will be answering questions. We have a number of pre-written questions that came in during the week, but if you want to, you can ask your question by typing it into the questions interface on the webinar panel, and we will get to those. Any we don't get to, we will definitely follow up with an email response. We will answer all the questions eventually. So let's get started. So the goal of the overall theme of this work is to move simulation forward with regards to product design. And if you're on this webinar, you probably already are a strong believer that simulation is extremely beneficial for design, but you have to make sure that what the simulation is telling you is something that you can use to steer your design. So for us, that means that your simulation is one, it's a stable simulation, it's going to provide reliable results, and that you can trust the direction that the simulation is taking your design in the sense that your answers are accurate within the bounds of your analysis needs. So this has a wide variety of implications. One, you have systematic errors, like how well resolved is the geometry with respect to the physical device, the as-built device. Usually we're modeling a simplified design, and that imposes errors on the result, and we want to keep those bounded. Typically today we're addressing those types of errors by including more and more geometry fidelity in our calculations. So we're using fillets on turbo machinery. We're modeling trailing edge treatments on aircraft. We're increasing our geometry fidelity to reduce that error. The other one is modeling error. We know that we rarely can do a full up direct solution to the Navier-Stokes equations. We're always modeling the turbulence scales, but we've seen a lot of progress over the fidelity of those and the applicability of those to our production workflows, and so that too is being driven downward. But the final piece of the puzzle is our mesh effects or discretization error, and we want to have a bound on it as well in this process. So all of these go together, and what we're talking about today is how to control your discretization error through mesh adaptation. And we want to do this in a user-independent way. You could always simply refine your mesh and make a finer mesh, but we want to do this in a robust, user-independent way, and that's what we'll be describing today. So I've got a couple of dense slides to get through real quick, and then we'll get into an example. But the idea is that we're going to examine the effect of going from the continuum realm of the Navier-Stokes equations into solution numerically on a mesh. And what happens there is we always impose, regardless of your solver, you always impose a known solution at a certain level. So for instance, if you look at a Taylor series expansion here, that's a perfect continuum expansion if you have infinite series. When we design a numerical algorithm, we always drop a number of higher order terms that's selected by the solver to be truncated. And that is the source of discretization error, the truncation of those terms at the time that the numerical method is described. And we can use that to estimate what the effect of that error is. So if we drop from the continuum realm on the top line into the discrete realm below that on an individual mesh, we have the concept of the distance h between 2 degrees of freedom on your mesh. You may hear us talking about this being a mesh edge because ANSYS CFX stores the solution data at the vertex, but this would be equally valid for a self-centered method where the H vector is between two cell centers. So keep that in mind. And for a second order solver like ANSYS CFX or many of the production solvers out there, the solution is assumed to be linear between the 2 degrees of freedom. So if we want to interpolate the solution between them at the mid-span location, we have this, what we're calling the low order interpolation form at h/2, which is, in this case, simply an average of the two nodal values. However, the solver is also going to provide the gradient at those locations. And from the gradient and the solution value at the degrees of freedom, we can construct a cubic interpolation. And that takes the form of what we're calling the high order interpolation at h/2 there. So if we subtract those two, we get an estimate of the discretization error at that midpoint through interpolation. And the nice thing about it is it only involves your current mesh, which gives you the H term, and your solution gradients. And these are all readily available in a post-processing sense for your solver. Visually, what this represents, if you look over here on the right-hand side, is you have your notional continuous solution variable in red, or you could think of it as the interpolation in high order, and you have the actual assumed discrete solution provided by your solver in black, with the gradients provided by your solver in the cyan colors. And maybe this is a pressure recovery on a wing or something like that. You could think of it that way. And the error is the difference between the continuous solution and the discrete solution shown here. And we're trying to get an estimate for it using interpolation. Okay, we will use this error estimate to construct a adaptation sensor to tell us where the mesh is deficient with respect to the current simulation solution. So we have our anisotropic tensor brought from the previous slide that is our estimate of discretization error. And now this is the source of discretization error. This is not the full discretization error, of course, because there's no advection of this term, but it is a source of it, and it's been shown that controlling the source of discretization error is an excellent way of controlling the entire discretization error. So we want our sensor to be proportional to this, but in this form here, it's a full tensor, and we're going to be doing isotropic mesh adaptation with respect to the current mesh. So we want to convert first to a scalar. So the first thing we can do is simply take the magnitude of these vector quantities that we're multiplying, and that gives us something that's proportional, but has a lot of deficiencies. One, it has no boundary layer protection. So our well-constructed boundary layer mesh would be attacked by this sensor. And through inspection, we can realize that we've already constructed a quasi-structured boundary layer mesh suitable for our chosen turbulence model. The growth rate and the initial height are something we don't want to change. So we want some boundary layer protection, and we can do that by taking the directional derivatives with respect to the mesh edges as the second term there. And that solves that problem nicely. But there's one final issue. We don't have protection for solution discontinuities, things like shocks or maybe multi-phase simulations like an edge going across a bubble in a cavitation, something like that. So we need to protect against very large gradients. And sometimes this is called the multi-scale problem. You want to attack multiple scales in your problem. And so we can solve that by raising our magnitude of our edge length here to an exponent p. And that typically is in the range of 2 to 4. And what that does is very small edges with respect to the average edge in the mesh will be de-emphasized. Larger than average meshes will be emphasized. So that provides the type of behavior that we're looking for and is our final form of our adaptation sensor. A final note, this kappa term out front is a leading coefficient. That's a field variable. This is where you would put your output-based adjoint sensitivities if you have them. In this current work, we're not doing a solution adjoint, so kappa is equal to unity everywhere, but this is where you would place this. And then the last comment is that this sensor form works very well with superposition. So it does require you to select a solution variable phi, but you're able to select multiple. And on that note, what is a reasonable solution variable to use for adaptations? Well, it's problem dependent. Hopefully you have a good feeling for which physical values your device is most sensitive to. Some suggestions that we've used successfully in the past are, for external aero, we'll use Mach number. It will capture the fluid energy as well as the momentum very well. For a heat exchanger, you're looking for that energy transfer to and from the fluid. So enthalpy is something that can be used. For mixing devices, both things where you're looking at heat transfer and energy transfer, vorticity magnitude or turbulent kinetic energy are good ones. That's similar for turbo machinery as well. Again, it's you're looking at how much energy is being given to the fluid or taken from the fluid, momentum energy. And then in multi-phase flows, you may choose density if you're looking at some kind of bubbly flow or something like that. It may mean that density is most important to your simulation. Paul, did you have anything to add there? I know you've had a lot of experience with these calculations.
Well, I've had some. Yeah, certainly for turbo machinery, we've looked at velocity magnitude and their gradients and turbulent kinetic energy, and they actually did pretty similarly. So in fact, I think in some of these cases, it's not so critical what variable you choose there, and it's, as long as it's something that's reactive and sensitive to the flow, and Mach number, velocity, and turbulent kinetic energy, I think in a lot of the cases we've looked at, done fairly similar impact on the mesh.
Steve, you've done a lot of external aero. What comments could you add?
Well, one that's not shown here is pressure that I've used when I'm doing some in-visit calculations. It won't develop a wake refinement pattern like the Mach number or velocity magnitude does, but in in-visit flows, pressure is the predominant variable that most people are looking at.
Good point. Good point. So the image that you're seeing on the right here is an impinging jet on a heated plate. This was a calculation that Paul and I worked on in developing this, and for there where we were using turbulent kinetic energy because you have the Reynolds analogies for heat transfer and viscous forces. So it worked really well for us. So this is the velocity field. You have a round jet coming vertically down and impinging on a flat plate. And on the next slide, you'll start to see a little bit of the adaptation procedure. So we have our sensor equation at the top there. That's a field variable, it's a scalar, and we'll compute that for all of the vectors between degrees of freedom in the mesh. So for ANSYS CFX, those are all of the mesh edges. And we're going to compute it for each edge, but we're going to push the maximum value of each edge S calculation to the mesh nodes, the vertices. It's going to make management of this process much easier if we push it to the vertices, keeping the maximum value of each incident edge collected at each node. Once you have that field, the strategy is actually quite simple. You simply need to define a threshold value above which we will be performing some mesh refinement in order to bring that value of that sensor down. That sensor is directly proportional to our discretization error, so we want to minimize that. A very simple selection of the threshold value could simply be the average of the range. If you selected that, you would work on the worst discretization error in the problem, and you would bring the discretization error down if you simply selected the average every time. However, that's can be wasteful and also can not really allow you to assess how far along you are with respect to convergence of the entire solution. So we're going to talk about something called mesh complexity, and we'll use complexity to actually select the threshold. But once you have selected a threshold, you can use the current value of the sensor at the node and the incident mesh edge length, which gave you that sensor value, in relation to this threshold value to come up with a new target edge length locally. And if that sensor value is greater than the threshold, we'll do so and we'll export that new length scale and location to a point cloud data set. So this will be a very sparse data set. You see an example of it here on the right, where it's only outputting the point cloud where the sensor has indicated that we have a larger than the threshold value of our sensor. So it's very sparse, and the Pointwise mesher is able to import this and construct a new mesh using this data. It will do so by remeshing using your original mesh topology. Now, I do want to make a distinction in the Pointwise terminology. The topology is your basic outline of your mesh. It's where your surface patches and edge curves are located, and then those are used, of course, to build the volume mesh. And this is what we call the topology. This is in contrast to the mesh connectivity, which is the local element structure and connectivity in the current existing mesh. So we will be removing the mesh connectivity, but keeping the mesh topology and rebuilding a new mesh which conforms to the updated size field given by the point cloud. So the idea of controlling mesh size through complexity, where this comes from is the realization that having a target edge length, you can treat that as a continuous metric field, which is doing local volumetric scaling throughout the field. And we can take this continuous mesh complexity and we can actually do a discrete integration of it over our existing mesh that we're doing this adaptation to So we do one discrete integration using our current edge links. So it's a volume integral of our current edge links and a volume integral of our target edge links. And the ratio of those two is going to be the ratio of the degrees of freedom in the updated mesh, as long as your mesh is conformal to that target edge link field. This provides a really nice control because we can say that, for example, we want the mesh to grow by 30% during the current adaptation cycle. And by computing this volume integral, we can then iteratively compute the threshold value of our sensor, which will give us that target growth of 30%. And that's what we've done in all of the examples shown here. And it's proven to be very stable in the process of only growing the mesh by a fraction every iteration. On the right here, you see that updated mesh coming from making a conformal mesh from the topology for the updated size field driven by that point cloud. Okay, a final note about this process. Why remesh? Why not just change the mesh in place? Well, changing the mesh in place may be really efficient for modifying the mesh connectivity, but you lose many things. One, you lose the best practice meshing strategy that you have adopted. You lose the manner in which the geometry was resolved using paving type routines. You also lose your near wall boundary layer quasi structured stacking. If we're going to do local adaptation kernel metrics, you're going to lose that quasi structured nature of the boundary layer, and that is something that the turbulence model and solver are depending on. So we want to maintain that. The other thing is that we're maintaining geometry associativity. And this is really a key point. If we refine the mesh, but we don't stay on the geometry, then we don't know what systematic errors we're adding in our attempts to remove discretization errors. And that's a very important point to remember, is that by remeshing, we are staying on the geometry exactly. And while there's techniques for reprojecting an existing volume mesh onto the geometry, Steve can tell you how difficult that is to maintain mesh quality when you do so with highly packed viscous cells. The projection is no longer a very trivial exercise. You usually wind up tangling the mesh or forming, at best case, valid but extremely poor quality cells. And then one thing about the remeshing method is it will attempt to conform to the new size field, but it's going to do so while maintaining element quality. All of the algorithms involved are going to perform their jobs while also with keeping an eye on element quality. And that's really important for the efficiency of the solver while we're doing this user-independent method. And finally, in Pointwise, this is actually, the remeshing task is actually automatic. Once you have defined the mesh topology on your first baseline mesh, remaking the mesh from that topology with the updated point cloud file is actually user independent and is something that can be done with a batch script. Okay, now on to an example. Paul, would you please lead us through this?
Sure. So one of the examples we did was a turbine rotor from the Aachen turbine at RWTH. And it's a simple case here. We're just solving the rotor, but to show you how it works. 41 blades, 3,500 RPM. We specify the inlet total conditions and the outlet static pressure. And for this case, we did some experiments, but what we'll show you is the adaptation sensor was based on the velocity magnitude. Oops.
Yep, sorry.
Sorry.
Yeah, take it back, Paul. I'm sorry. I was attempting to look at something on my side. I did that.
Yeah, there we go. go back up one. There we go. So our adaptation variable is velocity, and adaptation rate. We did some experiments with this P coefficient of 2.5 and 3, and we'll show you a few results of both. And we stuck with complexity ratio increase of 30% at 1.3 for all of these simulations. So our initial mesh is very, very coarse. It's under 500,000 nodes, 355,000 nodes. Using T-Rex, it was a combination of hex, tet, prism, and pyramid elements, as you can see here, and was built with the best practices given the fact that this is such a small mesh as an initial point, but we're going to rely on adaptation to enrich this mesh as we go. And I think an important point here, and leading back to some of the quality and so on that Nick was talking about, because we're going to rely on the mesher to generate the boundary layer resolution. No one needs to run a CFD solver to know the size of the boundary layer and the thickness of the boundary layer. We know that from the Reynolds number. And so why not put that in right as a starting point in the mesher? We shouldn't be relying on adaptation to automatically produce our boundary layer mesh. In fact, maybe your turbulence model dictates, well, we need a y plus less than 1 to resolve transition, or maybe the turbulence model can't handle that small of y plus and needs log law wall functions. So maybe we need a y plus of 30 or something. So this is input, and I think it really takes away a lot of challenges for adaptation if your mesher and the engineer is taking care of what y plus does he want to begin with in his mesh. So we generated this with a y plus of 4.5. Here's a whoops, we got a bit of lag happening here, I'm sorry. Try and get back up, there we go. Nick, we might need you to do the slide advance. Let me see if I'll do it one more try. There we go. So this is a cross section of what the initial mesh looked like generated with T-Rex. And you can see there's stacks in the boundary layer that go out quite far into the volume of hexahedra elements. And then there's a variety of different element types to fill things in the middle. And there is boundary layer resolution. You can see it on the hub, on the surface of the blade, and also up in the tip gap. So that's the initial mesh, just to give you an idea. But again, very coarse. So here's what convergence looks like, typical convergence. So what you're seeing here is the residuals of the mass and momentum equations. And the initial mesh is run for here to about 200 iterations. And then the first adaptation occurs. And so this is cycle 1 of adaptation. The solution field from the previous mesh is used to initialize the solution on the new mesh, and the new mesh has been generated with the adaptation edge length field in place. And so you run to whatever level of convergence you wish. This is something you can choose to adjust. How tightly do you need to go on each of these adaptation steps? And this can really save you a lot of CPU time. But you don't want to go too coarse or too loose on your convergence, because then you may be introducing some chaos into your adaptation. But you don't need to go too tight either. You might want to save your final tight convergence for your last cycle when you finally have the mesh you care about. Oh, okay, I see what my problem is on changing slides. Okay, so here's a snapshot of what the mesh looks like after 10 adaptation cycles. And this is at mid-span through the blade, but it's actually quite interesting. You can see the boundary layer meshing that's being generated by the T-Rex mesher is dominating at the walls, but it is eaten away into it in some places here right near the trailing edge, where the adaptation edge length said adapt. But down inside the boundary layer, nothing had to happen. You can certainly see the wake. Now, if you did a different operating point, you would have your wake adaptation on a different angle, depending on which direction the flow is going between the pressure and suction surfaces where they mixed. Here's the wall shear stress on the hub, and you can see the vortex that's happening and rolling up right on the hub in front of the leading edge is causing quite a disturbance to the wall shear stress. What's really nice about this overall approach is the adaptation can really pick up some subtle flow features in the adaptation. So there's the mesh adapted, and you can see it is definitely being sensitive to where that wall shear stress was affected by the vortex sitting out front of the blade on the hub. And there's a 3D view of where that vortex is sitting, so you can kind of see right where the flow is coming up at a particular line of streak lines, stagnation happening. There's a bit of an angle of attack here, and then there's this hub vortex forming, and that corresponds exactly to where the mesh has been refined. Now that's a subtle flow feature. That rotation that's happening there, the vorticity, is a lot lower than the main passage velocity gradients, but it's picked up quite nicely here. And in fact, it's picked up quite quickly. After only 3 or 4 cycles of adaptation, you start to see this. Here's a view from the trailing edge of the rotor, and it's showing the different vortices. There's a hub vortex, and there's a shroud vortex from the tip flow and from the horseshoe vortex at the front, and they're all kind of combining into this fairly complicated secondary flow features, and we're looking purposefully right down the center of that secondary flow vortex. And if you plot the mesh here 3 times just for clarity, you can see the mesh. First of all, it's been really sensitive to the tip leakage flow. It's resolved the tip flow as it spills over the top of the blade, and the mesh has actually picked up these secondary flow features of the vortex coming out to the trailing edge. So very subtle flow feature, picked up very nicely. Again, you can see the boundary layer meshes has been nicely preserved on the shroud and on the pressure and suction surfaces of the plates. There you go, just a picture of the mesh. Last couple of slides on this is a wall clock time. What does this all mean to the money that you're paying to get your solution? How much CPU time are you incurring? So there's 2 lines on this graph, and we're plotting the wall clock time versus the number of mesh nodes that have been solved. So this is adaptation 1, adaptation 2, adaptation 3, adaptation 4. And what this dashed line is giving is the CPU time that was taken for that particular cycle in the adaptation. So when we got to this mesh right here, it took this much CPU time to touch up the solution, starting from the initial conditions of this mesh and so forth. The blue line is the sum of all that CPU time. So this point right here is the sum of all of the CPU times taken for each of the cycles involved in the mesh adaptation. Now you get a bit of a multi-grid effect here. These first meshes are very quick because they're coarse, and it seeds the next solution with a finer mesh with almost the right solution, just has to touch it up a bit where you've added some resolution. Now, quite shockingly, for this case, if you took any one of these meshes, so suppose you took this mesh right here, that's around 8 million cells, 8 million nodes, and you just solved on that mesh from initial conditions, that's what this red dot is right here. So the total CPU time to solve on this mesh is more solving cold start on that mesh, if you somehow were able to generate that mesh yourself with that kind of resolution, than the total CPU time it took using this adaptation approach, where you restart from a previous known solution with your adjusted mesh. And finally, out at 15 million nodes, basically it was the same CPU time between starting cold on the finished mesh versus the total accumulated time for adaptation. So this really shows it's competitive in a CPU sense. It's not causing you some huge penalty getting to your adapted solution. Okay,
thank you,
turn it
Paul.
over to, yep.
Yep, we'll give this to Steve now.
Okay, now it's my turn. So up to this point, everything we have been talking about is H adaptation, H being the measure of the mesh length scale using the point cloud, and we'll refer to that as the H cloud. So the work that I'm going to show now, everything that has been shown up to this point can be done with production Pointwise. The work that I'm going to show now is work that we're doing in research with a NASA Phase 2 SBIR with University of Tennessee, Chattanooga. We're doing H and P adaptation. So we're going to follow the same kind of practices that we just described for the H adaptation. And the example case here is an Honor M6 wing with an Euler solution. And we're going to modify it a bit, though. We're going to use a shock sensor to identify where the discontinuities in the flow are. And we're going to generate an H cloud for those locations, because that's where you really need to refine the mesh to get the accuracy you need. We'll also be cognizant of any geometry discontinuities. So all other locations in the field, we're going to use that adaptation sensor to define a change in the order of the mesh. So in this case, usually it's H and P. P is the order of the solution space. In the meshing world, when you're curving meshes, that's usually referred to as a Q order, because you can have a different mesh order as between the mesh and the solution space. So the process is going to be perform the linear mesh adaptation with the H cloud as we've just described, and then take that mesh and feed it to the research code I've been working on. I call it HP curve mesh, and it's going to be fed a Q cloud where the solution has been examined, and a cloud that specifies a local order of the element is going to be specified. Nick, would you advance the slide, please?
There we go.
Okay, on this image, there's the picture on the left is a image of where the shock detection sensor has identified where there are discontinuities in the solution space. And this is the lambda shock that's typical on this on our M6 wing. So everywhere you see a volume element displayed, that's where the discontinuity has been identified. On the right, a H cloud has been generated for those locations, specifying a new size parameter that is fed into Pointwise using the linear adaptation. Next slide, please. So that's the H cloud. The P cloud is where you're specifying the order of the polynomial. And in mesh curving, if I was to generate a quadratic element, it basically involves adding midpoint nodes to the mesh. So a tetrahedron will now have 10 points in it. It's going to have the original 4 nodes and then an additional node at each corner, each midpoint of the edges. And then you can go higher, you can go cubic and quartic. On the left is the target element sensor, and the colors aren't the same between the left and the right, but on the left where there's green, where there is dark blue, it's indicating basically linear, and then elevated to cyan for quadratic, and all the way to quartic is red. On the right is the point cloud has been generated for this case. You'll see that there's points that are in the shock region. They are actually specified as linear, so they're Q1, they're green. And the refinement, the elevation process will try to enforce them to maintain a linear elements. The yellowish color is the quadratic elements, and then cyan is cubic, and then finally quartic is the cubic is magenta and quartic is cyan. And there's a transition. You don't jump from one order to 2 orders higher. So there's a nice adaptation between them. In this image, you see on the surface the coloring of the mesh based on the polynomial order. So in the shock region, you can see the mesh has been refined. In the smoother regions on the upper surface, you'll see that it's yellowish, so that's quadratic. On the leading edge, you'll see the cyan, which is quartic, and then next to it is magenta. So this is, and you can also see the nice smooth curvature on the little inset image. So this is the adapted mesh, and it's also demonstrating that we took a solution space from an inviscid solution. We actually adapted a viscous mesh, because you can see the viscous layers on the symmetry plane. Next slide. So the folks at UT Chattanooga, Kadami Srinivas and James Newman, have been developing a finite element solver named FunSafe. and they are working with us on this NASA SBIR. And so the plot here is showing a solution from a completely linear mesh on the left, Q1, a completely quadratic mesh on the far right, Q2, and then in the middle is a mixed order mesh that has both quadratic and linear elements in it. And it basically has the solution from the fully Q2 mesh, but there are almost 5 times fewer degrees of freedom in that mesh. So this demonstrates that you can do H adaptation and combine it with P adaptation and get an accurate answer in your solution vector. I think that completes the HP adaptation.
Yes, thank you, Steve. Okay, that's the end of our prepared slides, and we do have a number of questions that have come in. Thank you for those. We will start with one I would like Paul to field. Written in was, what does the solver need to be capable of in order for this process to work?
Right. Well, a few things. Well, first of all, it needs to output the value or gradient of the important variable that you're going to use for your sensor, and that's straightforward. And usually the solver will compute the gradient of that as well, so it computes the best value it can for the gradient given the numerics it has. But then what it needs is some other things to happen. So a key enabler for this, for computational efficiency, is the solver must be able to interpolate an incoming initial condition field from one mesh onto the new mesh. And if that's done robustly and smoothly and efficiently, that really is enabling in terms of CPU time. The process has to be robust inside that solver. It's got to happen with no user intervention. This has to be implemented in an automated loop. Doing it by hand would be fairly painful to start and stop these components. You want it to happen automated, and prerequisite is that the solver runs with no intervention. You need linear scalability with mesh size. This is a combination of the numerics that's inside the solver, something like additive correction multigrid, but also you need to perhaps increase the number of CPUs. You need parallel processing to work well with it, so you can manage your overall CPU time. And finally, you need some kind of controlling process. We have our controlling process that we've developed together with Pointwise. Run the solver, run the adaptation point cloud analysis to generate the point cloud, run the mesher, all of this in the background, and then repeat until you get to some convergence criteria. Typically, we've used convergence criteria looking at the percentage of the mesh nodes that are actually being adapted. And this starts off small, maybe only 20% or 30% of the nodes, but as the discretization error becomes uniform, which is what we're driving it to become, then more and more of the nodes are involved in the next adaptation step. So we would stop, let's say, when 90% of the vertices are indicated for adaptation. And lastly, we've chosen to use 2-point clouds most of the time for any particular step we're making, and this really helps smoothness of the process and stability of the process as well.
Thank you. There's been a few questions about meshing types, and I'll try to select one that I think is representative of many questions that have come in. Does it matter which mesh type I'm using? So TET, polyhedra, or hex dominant meshes all have strengths and weaknesses in the solvers, geometry representation, etc. With regards to adaptation, what are the implications of your individual mesh type, be it hex dominant or TET or poly? And is one better than the other? So I think we all have comments about this, but I'll start. I'll say that definitely the mesh type is something that you need to be aware of. Your particular solver is going to perform better on a given type of mesh. I mean, we would all love to be running structured multi-block, perfectly flow aligned hexes. That would be the ideal scenario. But we do have schemes that are hex dominant and so forth. And which one's going to be better? is going to be solver dependent. The nice thing about the mesh adaptation scheme that we have presented here is it's largely orthogonal to the choice of the mesh that you take. The mechanics of generating the sensor that we've described are going to tell you the deficiency of your chosen mesh style on your chosen solver, because you're using your solver's output to tell you what it believes the mesh quality is with respect to the solution. So an important point is, in a way, it doesn't matter. I mean, it does matter, of course. Your solver is going to do better on one type than the other. But with regards to adaptation, it's something that you can largely make the choice of independently. Make the choice based on your solver's need, and then go ahead and perform adaptation. Steve, anything to add there?
Yeah, there's been some work recently using the voxel style mesh in Pointwise to do LES calculations. They seem to do a better job of that. Of course, this is a finite element solver, but it's just an example where you can choose a different volume mesh style and apply this adaptation technique and adapt your mesh. So it's true that the adaptation is going to, the accuracy is going to be a solver dependent issue, and the solver is the one that has to answer it. But this process allows the flexibility of applying adaptation to any style of mesh that is created in Pointwise.
Good point. There's some interesting research being done on hybrid RANs with LES and adaptation right now, and it's really interesting. I mean, it may help with the gray area problem of transitioning between the RANs and the resolve scales. That's an interesting research topic to pay attention to. Paul, what would you add to this question?
Yeah, I mean, I guess I'd echo a lot of what's been said, but I think a key point is not in particular what mesh style has been chosen, but that the mesh adaptation process sticks with that style. So otherwise, you can really start heading into some chaos. So you know, if you're doing it manually, you want your meshes to be self-similar as you refine things, and this is a natural outcome that's going to happen here if you're remeshing with the same input deck all of the time. Your mesh topology that you've chosen to begin with will persist, and now your enrichment is producing, to the extent it's possible with an unstructured mesh, a self-similar mesh. And I think adaptation is really the great equalizer. What we've seen in a number of cases we've tried is, even if you start with a not so good mesh, maybe you have a mesh that at the top of the boundary layer into the volume mesh above that, there's a big jump in mesh size, which is difficult to control most of the time. But as soon as you start adapting, that jump is attacked. And then you have a smooth progression in your mesh length scales as you go from the top of your boundary layer into the volume. So in a way, it attacks these kind of deficiencies as well.
Good point. I have a couple of questions which are a little bit related. One is, how do you account for mesh sensitivity and adaptive meshing? And I think what was meant by that is, if you have a coarse mesh and you adapt to features on the coarse mesh which may be poorly resolved, how do you know that you're not driving the solution in a direction which is not what you might have gotten with a fine mesh in the beginning? And to me, the related to that is transient simulations or unsteady simulations. So where you have flow features which are migrating around, what would be done there? So I'll take a first stab at this. So firstly, you are correct. We are adding another nonlinearity into the system here. We're changing the mesh as the solution is converging. And I mean the solution on the fine mesh, the ultimate solution is converging. So it's important that you start with a baseline mesh which has certain best practice qualities. You want something that the models are supporting. You don't want to go so coarse that the model is invalid on that mesh. You want to resolve your geometry initially, because that's informing your flow field. So we always start with a coarse but best practice mesh. So it's not going to be 5,000 cells. It's going to be a larger mesh that is resolving the geometry to best practices, that is building a boundary layer mesh that the chosen turbulence model is expecting. This mitigates it. The other thing is having a strong solver like CFX, which is going to converge these individual cycles very well and robustly. And also the idea of bringing complexity in, where we're not allowing the mesh to change wildly from cycle to cycle, in which case the physics could start to thrash. We're controlling that growth in the sense that we can do this. And then I do have to circle back about something about transient, but maybe I'll let Paul jump in here. He ran all of these calculations. Maybe he can tell us how stable all of this is.
Yeah, well, in the cases we've done, we've seen it to be very stable, in fact, and we haven't explored a lot how crudely you can solve each mesh along the way. We've actually solved it fairly tightly, but even doing that, the CPU hit, as you see, was minimal, because you're seeding that next solution with a really good solution from the previous mesh. And because the meshes are self-similar in a way, in particular, not only self-similar, but perhaps even identical where the boundary layers are and where the geometry is resolved, because that's been specified up front as part of the meshing process. You know those flow gradients. You know what's going to happen in a boundary layer. We don't need to rely on adaptation to come up with that boundary layer resolution. So I think all of those things together really help for to make things stable, and a key to it all, really a robust solver, and having a good interpolation between the different meshes.
Nick, I'd like to add some comments here. What we've been describing here is what's normally termed a feature-based adaptation scheme. If you have an adjoint solver, output-based solver, then you can actually introduce the sensitivity of the mesh through the adjoint output variables and have it converge to the proper mesh in a consistent manner. If you pick the wrong adaptation sensor, then you may be driving it to the wrong mesh. So it's really important which adaptation sensor you pick.
That's a very, very good point. Regarding the stability of this steady solution, and also crossing over into unsteady simulations like vortex shedding, one feature of the point cloud approach that I didn't call out originally is the fact that these point clouds can be used in combination. The method of generating what we call the size field, the continuous size field in Pointwise for meshing, is independent of the number of point clouds that you have. It knows how to do the set intersection, if you will, of the point clouds. And so I know that Paul found that even the steady cases were more well behaved if he kept the current and previous point clouds around. And the reason for that is because meshing is a binary choice. Often, do I add a point or do I not add a point? That's a binary choice. You can get into some oscillation between these cases where it adds a point, then the next iteration takes it out, and vice versa. By keeping 2 point clouds around, we saw that largely eliminated. And you would do the same thing for a transient case. If you have a transient case, you would need to monitor the period of the transient, and you would want to keep around that many point clouds. And this would allow the entire region behind a bluff body, for instance, to be refined uniformly to capture those vortices. Now, if you had a longer period unsteady case, you may choose not to do that. You may choose to essentially track those features as they're propagated downstream in some large environment, maybe like a wind turbine or something like that. In which case you would only keep around a couple of point clouds, as we did in the steady cases. And in this case, your mesh is going to be refined and then de-refined as your solution progresses in time, as those features are transported downstream. So really the approach works with either. If you do have unsteadiness, you have to be careful and track that and take appropriate action as to how many of the point clouds you keep around when the mesh is remade conformal to those point clouds. Paul, anything to add there?
No, sounds good.
Okay. Maybe a real quick one, Paul. Can you just give a little specifics about what did you have to do as a CFX user to make this work? Is this something that is done in the solver? Is this something that's done in the post processor? How does someone start using this today?
Right. So in the CFD solver itself, the only thing that you need to make sure is that you're writing out the gradients in the result file of the variable you care about. So they may already be there, but you may have to choose to force to have them come out. Once those gradients are there, we have a process that sits in between CFX and Pointwise meshing, and that process really takes care of those first 3 or 4 slides you went through, coming up with the mesh sensor, and then boiling that down into a point cloud or set of point clouds. And really that's it. The interpolation is already there and built in. You don't have to do a thing for that to happen.
Thank you. One for Steve regarding high order curved meshing. What's the maximum order that Pointwise curved meshing supports, and what basis functions are you using for these elements?
That's a good question. Pointwise is basically a mesh generation program. So we are dealing with geometry, and we are using Lagrangian basis functions up to polynomial degree 4. So the distribution of the higher order nodes is an equal spacing frame of reference. And this is consistent with traditional textbook type discussions pertaining to higher order. We're using Lagrangian, and we know that they have a ringing issue on orders higher than 3 or 4. We believe the mesh order above cubic is probably not necessary, as the geometry is rarely higher than cubic. If you have an isoparametric finite element solver, that means the solution space is the same order as the mesh, and they don't tend to go higher than cubic in our experience so far. The non-isoparametric methods, such as the discontinuous Galerkin methods, will take an input higher order mesh, Q1, Q2, and then elevate it in the solution space, the P space, to much higher degrees, sometimes as high as 10. And so our position is, as a mesh generation company, we need to create the curved mesh using the common approach and allow the solver to modify and elevate and solution space as they need to.
Okay, thank you. We're coming up on our 1 hour time limit here, so I'll finish with a question that I think is really an open-ended question, but an interesting one. What role would machine learning play in mesh adaptation? And maybe I'll just seed the comments by saying that really that's a great question. I would like to see worked on. We're not actively working on machine learning at Pointwise right now, although we are actively keeping up with what's going on. I see a chance here to have machine learning handle some of these steering problems that we've talked about. We talked about how to declare convergence. We talked about how the mesh should grow with each cycle, and also what happens in unsteady problems. This is something that I think machine learning definitely could solve for us and take those decisions away from us and keep them, and put them into a rigorous mathematical space so that at least we get the same result every time. Those are my comments on that. Paul or Steve, any comments on machine learning? It's a scary topic, isn't it?
Yeah, I mean, what I would say for adaptation is to take solid steps here. So I mean, adaptation's been in probably all the commercial codes since the maybe mid 1990s and so on. But I think it's still not so well used and so popular for a lot of the reasons that we've gone through here. So you have to adapt to the geometry. You can't adapt to the original mesh and have it be useful. You need your adaptation to take account that you already know about the boundary layer and preserve that mesh generated with the mesh generator rather than with an adaptation process. You need it to be robust, and you need the whole thing to be sensitive enough to your adaptation sensor so that it doesn't way overly refine and become not useful. So I would say, taking some solid steps to go from the adaptations that have been out there for decades really and haven't seen much use, I would say, at least commercially. And can we take some good steps like we're trying to do here before going even further with something like adjoints being involved in there? Maybe that's already at the forefront, but machine learning would be after that, I would say.
You might also use it to further refine the value of that P parameter to figure out what makes a good exponent to get your adaptation and optimize your mesh strategy.
Yeah, that's a good point. That's definitely problem dependent and something that if you had a machine learning database on your problem of interest, that could be of great value there. Well, I think we better come to our conclusions. I'll start here. We've established that controlling numerical error is just as crucial to your successful design optimization as controlling your systematic error, such as which geometry decisions you're making, fidelity decisions you're making, and also which turbulence models you're selecting. And mesh adaptation is the way to do that in a user-independent manner. We've shown you H and HP refinement to control numerical error and how it can be integrated into a simulation workflow. We shown that the remeshing approach provides some benefits. It maintains geometry associativity. You have a consistent mesh topology so that your solver convergence remains high. And then we believe that in addition to all of this, this is a realizable path to user-independent simulation because we're also working on generating that best practice baseline mesh in a user-independent way. And so if you combine that with this user-independent mesh adaptation, you're now looking at something where the user does not need to be as highly involved. So we really thank you for your attendance today. If we didn't get to your question, we're sorry. We will be answering all questions. We'll send those out and post them. This webinar will the recording of it will be provided. And if you need to contact us, you can reach out to us on our websites, pointwise.com, icmq.com, and we will really like to get in touch with people who would like to see how this could fit into their simulation workflow. But with that, I will thank our panelists, Steve, Carmen, and Paul Galpin. Thank you both. It's been a fun session.
Thanks, Nick.
Thanks.
Goodbye, all. Thank you for your attendance.